Thank you. So today at the MedTechLabs, we are very proud to have Peter Noël, who is one of the leaders in the field of medical imaging, and certainly in the subfield, which we will learn more about today, of phase contrast imaging. And starting off at the fantastic institution Technical University of Munich, and then being bought out, I guess, to the United States of America. I'm still waiting for somebody to call. You know, we're all waiting for that call, but for Peter, it actually happened. And I think University of Pennsylvania did something fantastic, master stroke, and Peter is now in charge of the. Peter, please go ahead. We really look forward to your talk.
So, Mats, thank you for the kind words. Concerning the board out, I never expected that call either. So I think if you don't expect it, that's the best starting point. Can you see my screen?
Yes.
Yes, excellent.
All right. So thank you for the invitation. As I said in the time before we started recording, I would have loved to come to Sweden, and I promise to maybe do it even next year to visit again. So today's topic, we're talking about phase contrast and dark field X-ray imaging, and I will talk a little bit about the basic background, and then I will go and review a little bit what different groups and different sites had done, and also where I was involved, to give you a bit of a picture of where this current technology is with respect to clinical applications. So there's a lot more in this, but I will really try to focus on where is it with respect to getting to a patient. Here are my disclosures, and then to start, let's directly jump into the topic. So these are images which were published in 2013. These were some of the first in vivo phase contrast dark field images. And what do you see on these images? On the left, you see an image which all of you are very much know. It's a conventional X-ray image. You see that the bones are enhanced. Nothing surprising there. Then if you go to the image in the middle, you see a phase contrast imaging. And you directly can observe that the nature of the image is very, very different. What you see here, for example, where the arrow is also pointing at, is the trachea. So you see soft tissue contrasts. If you think about this, the first thing you have to do is forget about photon Compton effect. I know that all of you think day in, day out about photon Compton effect. Just for a little while, don't think about this. Think X-rays as a wave. And what phase contrast really shows you is something you may see in summer if you sit and drink a glass of water outside and there's an ice cube swimming in it, and you see the shadow of that ice cube falling onto your table, for example, and you see there is an enhanced edge where there's a phase change. Then we get also a third signal, which was actually only a little more than 10 years ago really introduced, that we can see this with X-ray imaging, and this is the dark field signal. Now, on the right, you see a totally different picture of the mice. The first thing which you see is actually that the fur gives you a lot of signal, which we normally don't see. And you see that the lungs give you a very strong signal. So the difference here is that this is basically showing you the scatter. So how did the wavefront and the scatter change, or how did the wavefront change while going through many interfaces? If you think about the lung, we have a lot of alveoli, and every time the X-ray beam goes through it, there is a wave optical effect happening, and basically this is what we're seeing here. So basically, to come back to our real life scenario, if you have a window and it gets dirtier and dirtier, at some point you can't look out to it, but there's still light coming in, so your wavefront is getting destroyed. So these are the signals. And I think this should encourage everybody to think about it, because I think you can directly recognize many applications. How can you measure this? So over the last 4 or 5 decades, many developments have been done it's important to first mention that actually Röntgen, in his original work, he mentioned that X-rays have a wave character and we should be able to measure this. So here on the left side, you see the four main ways of measuring these type of signals. The most simplest one, if you think about it, is number C, it's propagation-based imaging. Basically what you do, you have a refraction, which is very small because of the wavelengths of X-rays, and you put a detector in a very far distance away, and at some point, because the beam is diverting, you start to see these effects. But if you think about clinical applications, I mean, the first three have a lot of constraints which we will not be able to fulfill in a hospital setting. So the best candidate is grating interferometry, because also over the last 15 or so years, it has been shown by Pfeiffer as well as in Japan by Momose, that with gratings, you can use conventional X-ray tubes, which is an essential part to get into the clinic. So with this said, I will focus primarily on the grating work, and I will also talk about one of the more odd variations, which is speckle imaging. Is something actually we started to investigate some time and over the last 2 years or so here, and that will be more towards the end of my presentation. So let's talk about grating interferometry. To get you warmed up about all the things we're talking about, let's talk about interference. I took this a while ago from the Wikipedia homepage, and it just should remind you that, you know, if you have two waves and these two waves interfere with each other, depending on how their phases are standing to each other, you get a sinus curve with a much higher amplitude, or if you meet at a spot where it basically cancels each other out, you don't get any signal. And thinking about grating interferometric imaging, one good example to start with in your mind is Young's double slit experiment, which Young actually did in, I think, 1803 or 1805. I find it still amazing that this man proved this with a candle and a screen in his house. I mean, now if we think about how elaborate our experiments get, I mean, this man sat at night and figured it out. So what did he show, or what did he do? He showed that if you have an aperture like we have here, where you have two slits, an S1 and S2, and if you have a plane wave coming in at these two slit points, you basically have two new wave fronts starting. These two wave fronts move forward and they start to have interference with each other. And this, of course, brings interference patterns to your screen, and those are being built very similar to the first interference example I showed. So let's look at one example here. We have two waves coming, or two wave positions coming through. They meet at the screen, and at this point we will get a bright spot because the two are adding up to each other. Of course, we also have the opposite of this, and the opposite would be that we have a position where basically the two waves are canceling out and we get a dark spot. So we have both of these behaviors, and in the end, what we get, I mean, this is an experiment many of us probably did in school. You get an interference pattern on your screen, which basically shows how these two waves interact with each other. Can we do this with X-rays? Of course we can do this with X-rays. I mean, we have to remove the screen and get a good detector. We need an X-ray tube, and then this should work too. But there's more to it. Let's first think about what would happen if a wave front not only hits, like I said here, a double slit. Let's think about a wave front would hit a grating, which has not only two slits, which has n many slits. I showed a very simplified here, but imagine you would have a fine pitch grating in your wavefront. And what would happen is that you can measure something which looks like this. This is called a Talbot carpet, which happens due to the Talbot effect. And what you see here is basically if we would measure our interference patterns at each of these positions as a distance away from our diffraction grating. And what you start to observe here is that you get so-called self-images and repeatabilities. And the Talbot effect says that the wavefront hits the grating, and then at the Talbot distances, we get our interference pattern. So in the simplest case, we get at all the odd numbers, we see our interference patterns replacing. This, of course, has to do with the wavelengths of the incoming X-rays or wave in general. And of course, it has to do with the period of our grating. So there's a relationship here. So now, if we want to measure those interference patterns, we basically have to place our detector at one of the odd Talbot distances. So let's move a detector in. And now let's look for a second what we would expect to see. So here you see an image without any object in. So if we would have 2D image, it's very simplified. We would see something like this. If we now move an object in, you would get the changes in this interference pattern because the object will introduce some phase changes. And for example, I mean, this is very simplified. You would see an object scan which looks something like this. So now we know that if we measure with and without object, we can measure interference patterns, and we can use those to get information about our object. Now let's go back to the question, how do we do it with X-rays? So in an ideal world, you would just use an X-ray source, you have an object, you have your diffraction grating, and you have a detector. Unfortunately, this is not as simple as it looks here. The first problem we have is that most detectors we use, especially the ones we use in medical applications, the pixel size is by far too large to image these small interference patterns we want to image. So we had something which we call an analyzer grating, which basically virtually increases our pixel resolution on our detector. And we use this, actually also we'll show it in a second, to also scan the incoming pattern. On the other end, our X-ray tube is not 100% coherent, and it's not perfectly in as a beam you would expect. So to improve this, we also add a source grating, also called G0. And this basically is also a slit experiment. And you have all these small slits, and each of these you have to imagine as a separate X-ray tube starting a new wavefront. So this is the setup of a Talbot-Lau system. And how do we get to our signal? So to do this, we're basically have to analyze the incoming wavefront. And by do so, we move our analyzer grating to different positions. And basically for each of those positions, we will take an X-ray image and we start to record these images. And you can see here on the right, you start to see something which looks like close to a sinus curve, because we're basically going here and looking at the darker and brighter spots in this interference pattern. When we have this recorded, we can use a Fourier transformation or a real space way to fit the sinus curve through this and basically measuring our interference pattern. So this is, in a nutshell, how a grating interferometric setup works. What does it give us then? So, as I said, we have 3 gratings in this setup. There is a G0, there is a G1, and a G2. Now here in this example, you see we have 3 different samples. And the first one is a pure absorption object. And now, if you look at the total right here, you see the dashed line is basically what we always measure without an object. It's our reference scan. And then you see here the scan with the object, and you see how we see a reduction attenuation. And here is actually one of the great examples which exists, one of early Franz Pfeiffer's papers, where you see here the X-ray image, and it's water and sugar, and you see it looks like a normal X-ray image. Now, if we have an object which purely would give us a phase shift, we see how our wave front is moving sideways away from our reference scan, and we also see that here that there is a phase change. Now, if we look at the image, you see the characteristic differential phase contrast image, where we have a dark and a lighter side to the object, and then we get the last object. Let's assume there would be an object which only has dark field or scatter in it. What we would see is that our wavefront is basically slowly getting destroyed. It basically gets pushed together, and the image you get from this is what you see here. Basically, water has no, water has no small microstructures, so dark field signal is basically zero. But if you look at sugar, which has a lot of interfaces, you get directly a very, very strong signal. So for clinical applications, for many reasons, we'll go through this in a second, the most promising one right now seems to be the dark field signal, because we can get technically to it, and I think it has a lot of potential in clinical routine. I want to show you two examples before we go back to more clinical examples. Here you see a tomato, and on the left you see the attenuation image of a tomato, and on the right you see the dark field image of this tomato. And it doesn't need much fantasy to see the differences here. I mean, on the left, it's pretty much water, and so attenuation of this object is pretty much what you would expect. But if you look at the dark field image, you see that there's small detail structures in there, and because the X-rays have scatters there or get refracted, we start to see these internal structures. Another example, which I love, colleagues at this company did this at some point to prove, actually for food science, that this has a lot of application. What you see here is a cup of yogurt, and you see the attenuation image, and it looks, many of us don't look regularly at yogurt X-rays, but I mean, you see pretty much that you don't see anything. But if you look at the dark field, they stuffed some small foreign objects into the yogurt, like a small piece of wood, and actually not in this example, other example, they put a cigarette butt into it, and you can see, because the wood has a fibrous structure in it, you start to see this, and it becomes visualized. So how does this, what are clinical applications which we're directly thinking of? And the biggest one is definitely in the area of lung imaging, and that has been, I was in Munich, I was part of this team, but the bigger teams there, and Franz, who has been working for a very, very long time on this, has made this one of the main foci there, and I fully agree. I think this is one of the clinical applications where other modalities are not as strong, and at the same time, it's something which it seems to be achievable in a reasonable time. So coming back to this image here, you see the dark field image, and the lungs, the lung signal is really jumping at you. And you have to see it, that what you see here is a sub-resolution signal. We are not visualizing the alveoli structures. We're showing how the wave optical behavior changed in this area from a sub-resolution structure. So the bright, what you see in the image is not each alveoli separately, it's only how the signal changed in this time. And I think lung imaging is getting more important. I mean, this is something from last year which shows the mortality rate of COPD per 100,000 around the world. And I don't have to remind anybody on the call that we currently have a different lung disease which all keeps us awake at night. So I think lung imaging is definitely a focus, and something there's a lot which can be done. Now to show you a little bit how this transitioned over the last 10 to 15 years, here, this is an example of mice, which was done between the TU Munich, the LMU in Munich, and actually the German Mouse Clinic. And back then, they did many, many different animal examples. This is an emphysema model, and you see 3 mice, and you see 6, and 3 of these mice do have an emphysema conventional imaging very hard to detect any differences. If you look at the dark field image, in the upper row, you see the healthy lungs. In the lower row, you see the emphysema mice. And what you see here is that the signal reduces, and that's basically because of the alveoli structure changes. We, for example, get liquid in between them, or some of them also destruct. And because we have less interfaces for interaction, the signal goes basically down. They did a lot of work around this, but then the question about 6, 7, 8 years ago became, is this really translatable from this small animal to a large human system? There was a lot of doubt in this from many sides, but actually this is the time period where I was in Munich and was very involved in this project. And the first thing we actually did was build a large field of view system to show the feasibility that, first of all, you can do it with large fields of views, and also can be done with moving or in vivo objects. This is the first image which was back then taken. This is it's a fruit assembly. It's an in vivo fruit assembly you see here. This is the attenuation image, and this is the dark field image of this. And you can see that the lower end of the banana was squeezed, and the fibrous structure of the banana was destroyed, and the dark field signal basically disappeared at this point. The system originally was built, as depicted here on the left. It has conventional X-ray system, so an X-ray tube and a medical grade detector. It is 3 grating interferometric setup. And the way it was designed is that it's a slot scanning system. So we have a very small slot here, and the object, in this case depicted here, pig, will be moved through the beam. Gratings were built for this, actually in collaboration with the group in Karlsruhe, and there's also a publication about how these were made and how they were specified. Here you can also see a raw image of these gratings, or the fringes coming from these gratings. And after doing the fruit assembly, we went ahead and also imaged a pig in vivo. And here is the conventional X-ray image. You don't see, again, conventional imaging, no surprises to be seen. If you now look at the dark field image, you see that, first of all, dark field imaging or phase contrast imaging works in vivo for large objects. And there's 3 very interesting observations. The first is you see the lung, and the lung has a lot of signals. So it was a healthy pig, but we didn't expect anything else. The second observation is that if you look here, you see that there was some air in the stomach. This air does not give a signal in our dark field imaging. So, you would say a lung is air filled, but we see the signal is coming from the microstructures in the lung to show this point. The third observation is that you do see some artifacts here from the beating heart, but I think for a first try, I think they're very good. And since then, there is a lot of work actually has been also published on how to reduce this. As one more step on this, we also imaged the cadaver, so it's an ex vivo human image. Here you see the conventional X-ray image, and here you see the dark field image. First of all, the signal is not as pristine because the person was dead. The lung tissue directly started to change, but nevertheless, we had a signal, and some of these signal variations within the lung also correlated very well with the CT scan we took also in the same day, or actually in the same hour. So this project continued. This is basically the point where Mats said, I left and I went to UPenn. This is actually the last publication I'm still part of. So the team there, they started to build an X-ray system which could be used for humans. The big difference is that the human is standing in the system. It's not a system so it's very close to what you would expect in normal lung radiography. You can see here images of it's the lungman phantom actually filled with cotton balls to get some dark field signal. And you can see it's very, very nice image quality. And the very nice thing of this publication is actually this distribution plot down here. They analyzed 90 patients which were scanned, and the dose value was measured, and you see the dashed line is the mean value of all the dose values, and the reference value, so the one you're supposed to be in following German dosing law, radiation law. You see they're very close to this. So there's often a question, you know, additional gratings, how much does it increase the dose? So they could show actually for this system in a slot scanning setup that dose can be comparable to what is expected in X-ray imaging, with the additions that you not only get one image, in this case you get two, / you could also get the face image, which is probably not clinically that interesting in this case. They continued. I continued here, they continued there, and this was just a couple of weeks ago published, and you might saw the press releases. It's a great achievement for the group in Munich. They published this study of, I think, 60 or 70 COPD patients. They did in vivo, and you see in the upper rows, you see the dark field signals, in the lower ones, you see the conventional X-rays, and you can see with increasing COPD, the dark field signal goes away. I think this is probably a turning point, due to the fact that often when we talk about this, when we apply for grants, it's often said this is all a small play, this will never work clinically. And I think this is the proof point that this can work clinically, and there is a feasible way to do this. To point out, the Munich group is one group, but there's other groups working on this as well in different directions, and also in the lung directions. I think this is a quite interesting publication, which came from the group in Erlangen in Germany, which had an ex vivo lung, which they, from a pig, which they have a specific phantom, they can put it inside, and they looked at the image quality of the dark field images with different grating setups. So they used the gratings itself is a complicated topic to develop. The smaller the period gets, the harder it gets to get a small period with a very high grating height. And they looked at all these different combinations, or 3 different combinations, and actually could show that with these different grating setups, they could get dark field signals for each of them, which is it's good news. That means that there is room to work with non-ideal gratings. Because the gratings, I didn't mention this earlier, the gratings, for example, used in the Munich system are high precision gold gratings, which is a complicated and expensive way to develop or to also produce. So if there's other places here to look into grating technology. Then you see other developments coming up. There is this work, for example, from this university in Beijing. They presented in 2020 SBAE. They presented this system. So they built also a grating setup based on also existing technology. And they showed that they getting some images. I mean, here you see a rabbit and the lung. The image quality is by far not as far as the other groups have shown, but you see there's more and more interest, and more people and groups are starting to work on this technology. Let's talk about other clinical applications. I think there is much more than lung. I think the next best applications where we also see a lot happening is breast imaging. And this is due to multiple reasons. One reason is that from grating design, it is a bit more relaxed because we use not so high energies in breast imaging. So it's the engineering part is maybe a bit simpler to get to. At the same time, we see really great clinical applications. Here you see one work on the left where you see the conventional, the face and the dark field image. You see that these have very different characteristics. And multiple groups have shown that depiction of tumors can improve in the face signal, and also that the dark field signal actually can be very, very useful for characterization of calcifications in the breast. You see here on the right is a plot from Scherer et al., which look actually at different a different structure or microstructure of the calcifications. And they plot here basically the dark field signal as well as the conventional signal. And they see that they can cluster between these different groups, which apparently is medically very, very important because the type of calcification is a biomarker for how this will proceed for the patient. So if we would be able to early detect these, this would have a big advantage. There is work happening in Munich, but for example, there's also work happening on this in Switzerland with Philips together at some point. Mats is probably very aware of this mammography system because it's a silicon strip system. And they extended the system together with Research Philips into a grating interferometric system. It was already quite advanced, and it has many advantages. This could also be a slot scanning system because of the way the detector was already designed originally. So it was a very, very good starting point for them. They built, I think, a couple of prototypes, and here you see actually some examples of conventional phase and also of dark field signals. I think now this work has stopped to some degree because Philips has left the breast imaging world, but I think that Marco's group continues, and he has actually started this company which is trying to build a breast CT scanner, which I think is another application which probably has a lot of benefits, and I see there's multiple avenues of doing this. To mention others, the group in Madison, Wisconsin, around Wang Hongshen and Kai Li, have worked also on a breast system. As you can see in the upper left, they already have a system 1.0 and a system 2.0. And I know that they're started to do also clinical studies. Unfortunately, I don't think there's any results yet publicly available, but they did publish a Kiwi up here and also the pork belly, where they actually placed some microcalcification simulations in there, and they were also able to show that this is working. So you see there's many, many steps happening towards breast imaging. Another application is MSK imaging. And there is multiple directions one could think about. But in the dark field frame, it makes a lot of sense because if you think the lung, we had these alveoli structures which generate the signal. But at the same time, if you think about trabecular bone structure, it's also a source of generating signals. The first example is actually in the cartilage frame. This is a system from Japan, which Momose's group has developed with Konica Minolta. It's a quite interesting setup. The goal is to image the cartilage in between the finger joints, which is hard or almost impossible to image with conventional X-rays. You see here, it has a very interesting setup. You put your hand into it and the hand will be stretched apart. You feel a little bit like it's a medieval setup. I can tell you that a couple of years ago, I went to Japan myself and I got my fingers stretched too. It's a very interesting feeling. And they showed that they can show, it's very hard to maybe see on the screen, but they showed that they can show the cartilage between the fingers. And that this is a application. My last understanding is that this is limited to the market in Japan. Maybe we'll see those systems also around the world for cartilage imaging. The dark field signal also allows to look for gout. Here is results where the group looked at what would happen if we have a mice model and we would deposit crystals into the joint. So in the upper row, you see without the crystals, in the lower row, you see with the crystals. And on these are all projection images. It's very hard to impossible to see on conventional imaging, but on the dark field images, you can see the crystals or the change because these crystals generate a good dark field signal. They did a reader study, looked at this, and also showed that if you show radiologists both, it's much easier or it's very good for them to detect these. The other point comes back to the yogurt example. Here, the idea is to detect foreign bodies And I learned over time that this is actually a real medical problem. If the person says, I think there is a piece of wood in my hand because I got a splinter in there, it's very hard to impossible to see. Here in the upper row, you see attenuation images, and in the lower row, you see darkfield images. These were taken with the setup as you see on the left. There is a hand, and there were two types of foreign bodies included. There were aluminium as well as wood, and you able to see some of those much better with this technology. The last example, which is very advanced, trabecular bone and trabecular bone directions. So if you think about how an object generates small angle scattering, it depends on the direction or the shape of your scatter. If it's round, of course, the scatter will go into different directions, but if it has a specific shape, your scatter, there's a dominant scatter direction. So now if you go and you would take your object and you move it in your interferometer, like on an Euler stage, and look in all directions, you can start to generate tensors. And these vector fields basically show you the main direction of these scatterers. And you see this here on the hand on the total right. It's also done by the Klinikum in Munich. And you see that some part you have a very specific direction. So trabecular bone structure grows in this direction in the main part of the bone, but then towards the joint, it changes its direction. So basically these colors show you which direction the scatterer was. So it's a very advanced application, which is probably nothing we'll see in the very soon future, but it's also something we could see in clinical applications. So now you maybe ask yourself, that guy, he's talking the whole time only about projection imaging. What about CT? We want a CT. So I agree, of course we want to have a CT, and it is possible. And here you see examples from a small animal study where the upper two rows show you the conventional attenuation Hounsfield-based CT. In the lower row, you see the dark field signal of these different mice. These mice have different diseases, so you also can see that there's changes in the dark field signal. How can this come into a clinical system? And this has many challenges. If you think about only one aspect, I said earlier, you have to step your G2 to basically sense your wavefront. In the CT system, as you all very well know, we cannot stop at every projection, move a grating, and then move to the same projection. I mean, if we want to do something in CT, it has to become very close to what a normal CT does in functionality. One problem is the stepping. And because this, if you look at this, it starts to remind you a little bit also of spectral CT imaging. What happens is that we get these different signals coming in from our stepping. We do a phase retrieval, and then you get you do an FPP reconstruction. If you look at the comparison to spectral imaging, you will get your different energy bins, you do a material decomposition, and then you do a reconstruction. The idea which we worked on, or part of my group worked on while I was in Munich, was, can we not do something similar we do in spectral imaging, where instead of doing material decomposition and reconstruction, can we do a one-step algorithm? Can we directly go from projection space to our three signals without stepping in between? And we did this, or there's a paper from 2017 where we introduced the idea. And basically it's a intensity-based one-step iterative reconstruction, where you see here, we have a log likelihood term, which has a forward model and measured intensities. And then we have three regularization terms for each of the signals. This is very similar to things we do in algorithmic and advanced spectral imaging. But the forward model, of course, is very different, because we're not looking at photon Compton effects here. We're looking at these wave optical effects. And basically, this is the forward model where we have the visibility of the system. Line integral describes the dark field. Before this, we have a very classical attenuation integral, which describes this, analogous to any other CT imaging. And then we have this very tricky part here in the end, which describes actually the phase change. And because of the signal type, it's a cosine part here, which describes the phase change. This is a bit tricky to optimize because, as you know, if you have a cosine in something, it makes it quite hard. But we succeeded, and this setup works actually very, very, very well. Here we tested this with data from an ex vivo mouse, and you can see this was done without stepping. And basically the phase change measurements came only through different projection angles, because you see also phase changes in your phase patterns through this. And we were able to get the attenuation, the phase, and the darkfield signal. So I think on the algorithmic side, there is solutions already available for CT. I think on the hardware side, there's much more work to be done. It's very interesting. Yesterday, I was doing a little bit of a literature search to make sure I don't miss anything. And then I walked into this paper, which is actually very recent published. This is from also a group in Beijing, who built this tabletop system, which is a grating interferometric system. They say they're using a standard CT detector and a CT tube. They say it's not Talbot Lau, it's more like an edge enhancing or aperture type approach. I could not fully understand, to be honest, how's the reasoning for this, but they do show some images of an object. It's water with some plastic inside, and you can see that the phase and the signal, the scatter signal is working. So there is more and more interest in this is coming. To the end of my presentation, I want to talk about something totally else. And I was very intrigued by this for a long time. And when I moved here, I continued working on grating work, but we also started to look at speckle-based X-ray imaging. So this is very different, because your setup is basically a diffuser, which you place in front of your sample. And this diffuser in the original works could be sandpaper. And the particles of the sandpaper generate interference, and they basically generate speckles on your X-ray detector. This here is an example. We use a simulation tool to make, you get to see these type of speckles. Now, if you move an object into this wavefront, these speckles or this interference patterns change, and you can see here on the right, see for phase change, the speckle position would change. And also the phase front would start to destroy if we have a lot of dark field. I find this interesting for multiple reasons. I think it's very simple, because you can use some kind of a diffuser. I don't know if it's necessarily sandpaper, but it's something much simpler than gold gratings. And if you can do it for small objects, so I think this application in small in vivo imaging, for example, you could do it with a very small pitch detector, small pixels. So you don't have a lot of extra dose to small animals. You don't, especially if you have longitudinal small animal imaging, you want to be as dose efficient as you can. So I think that's why I was very intrigued to look into this. We started to do some work. If there's interest, there is actually a wonderful review paper from Soda et al. It shows how this actually developed over many years and how people moved this. We started to do some experimental work on this, and it's actually, as you can see, it's much simpler than many of the other setups. You see here that you can have sugar and water, very similar to the experiment we saw earlier. This is the attenuation image, this is the dark field image, and you see that the sugar gives you a much stronger signal in dark field. And you can also see here, we imaged basically a step phantom with different amounts of sugar, and you can see how the signal increases. So for small imaging, it works. To really evaluate this, also to convince people that this is one of the right things to do. For this application, we actually built a very elaborate simulation tool. And here we show some results of how this would work for really, I mean, as you see, small samples, and you see here the signal, and we're comparing these, the boxes are transmission or attenuation imaging, and the round ones are dark field signals. And you see that we have two types of different samples. One are PMMA spheres, the other one are SiO2 spheres, and you see if we get more samples, so we have more dark field interaction or more interference interaction, we get to see an increase in or we see that the dark field signal starts to build up here, and we see that we would not see any differences in our transmission imaging. We also looked at packing fraction, so how many of these small spheres can we get into it, and we also see that it doesn't really matter to transmission, but for dark field it matters. And we also look how different sphere diameters played a role in this. So basically showing for small objects, this should actually work, and it should give us the opportunity to image. As a last point to this, this is very interesting because what you're basically trying to do, you're trying to take two very noisy looking images, which are these speckles, and you're trying to compare them. And at some point, the idea came to us that this is actually something which happens in optical imaging. For example, if people track scent, how scent goes by a camera, like scent particles. So we looked more into it, and there's actually very elaborate AI solutions for tracking these changes. And we started to implement these to really try to track the changes in our interference pattern with the CNN, which allows us an advantage because in conventional ways, you basically do correlation between neighboring pixels. And by doing this, we lose resolution. With the CNN solution, we don't lose any resolution. And we'll present more about this actually at the upcoming SPIE meeting. With this, I think I come to my conclusion. I hope I could show you a bit about how this works, what the background is, and could also convince you that there is great clinical applications in this. In dark field imaging, I mean, the visualization of sub-resolution features like in the lung has a lot of application. Phase contrast offers also improved soft tissue contrast, which I think we'll see with more and more advanced instrumentation. And also the small animal imaging. I think there is applications which are very meaningful, maybe not directly translatable to large patients, but there is application to also help out there. Nothing happens alone. There's always a team of people who work with you or want to recognize them. And I thank you for your attention.
Thank you, Peter, for an excellent lecture. Very enlightening and impressive results, really. So questions to Peter? Well, I could start with a simple one. The speckle-based imaging, then did I understand correctly that then there is no gratings whatsoever, not even the G0 is required?
So it depends a bit on how you set it up, but the ultimate goal would be, to only, the joke I make in the lab is go to Home Depot, buy a roll of sandpaper, and you're good to go. If you go to places, to energies, or to fields of use where you get coherence problems, then you maybe need you would need a G0 as well. In my mind, I mean, if you have a grating which generates your interference pattern or a piece of sandpaper, there is similarities. You know, something is maybe less organized than the other one.
Yes.
Yeah, I have a question. I have my Ph.D. in X-ray phase contrast microscopy for 10 years ago, and so I followed this up to then, and then reviewing what's been done since then, it looks like there's many methods to reduce dose. This spectral method you were talking about is one. There seems to be also a large variety of phase reconstruction algorithms, like one called the back projection, I think, and then there's this statistical iterative methods, and there's a moire method. Is there like one method that's preferred now? Because I don't think anyone's really doing this stepping anymore.
So, I mean, of course, which one is preferred? The one my team developed is the one which is preferred. Let's start with this. No, I think actually, if you look at the back projection, then there's the moving window or the sliding window approach. And then there's also the fringe scanning approaches. I think they're all related to each other. And we see basically I mean, as we always are in science, I mean, none of us wakes up in the morning and says, you know, I have the idea and I never heard about this before. You know, things build on top of each other. I think the problem is maturing from time to time. And I can't answer you which is the preferred way of doing this. I think when we go closer, that more teams are more interested in it. I think many of the algorithmic teams will jump on it, and we probably will see a much better solution than the one we came up with. So I think it's still in this conversion phase. So I wouldn't say either of them is better or worse.
And what method did your group develop?
So the one I talked about today, we developed
stepping.
No, it's actually, so when you think about the reconstruction for CT, what we developed is basically that you directly go from images, which are basically counts, to your different phase signals by using a forward model, which describes the imaging process. For this, you don't have to do stepping because you basically detune your gratings a little bit, so you see fringes. And those fringes are changing if you go to a different projection or a different angle. And using this change, we use to get these different information.
Okay. There was also a paper about removing this G2 grating by modulating instead the G1. Is that, you know about that?
So removing the G2, yeah, I saw something, I believe that was from Marco Stampanoni's group. The question, if you do this, is how can you preserve your resolution in the image? That was my first thought when I saw this. Does this really work? I'll be honest, I don't know. It's an interesting idea, which is on the list to look at.
But still, you were saying sort of the dose is now, it's not a showstopper anymore for phase contrast X-ray imaging. It's not more finding clinical applications.
So I think that, I mean, we have to remain dose sensitive. There's no question. I think the one thing is the worst case, you need double the dose you need normally, but you get 3 times the signals. So I think you can argue there a little bit. The other point is what the Munich group has shown with their clinical studies is that they are basically around the German reference value, what you're supposed to have for the chest X-ray. So at least for this application, we can say the dose is maybe a bit higher, but it's nothing significant. So I agree with you, dose is not a showstopper, but I think we always have to keep an eye on it.
Okay, yeah, thanks for a very interesting talk.
Thank you.
Hey Peter, this is Mark Frontera from GE Healthcare.
Hey Mark.
Where do you see this playing out? Like if you look 15, 20 years out, phase contrast or one of these approaches ends up in the industry. How does that landscape look of MR, conventional CT, and one of these areas panning out? Where do you see the application space kind of trending to?
So I think there's a couple of thoughts behind it. I think so I think for each modality it plays out a bit different. Let's first talk about radiography. So radiography doesn't give you much information right now. I mean, if you think about it, I mean, it gives you information, but if you see these dark field images which have been published, it gives you much more. So I think you could almost see it as a lifeline for radiography. I think many, numbers of radiographies are going down in many places, but I think this is actually a technology boost which gets radiography back on track for a longer time. Now, if you think about CT, so first of all, I mean, you solved the photon counting problem, so you need other work. Let's start with that. The second and more interesting point there is that, first of all, CT, of course, is good in lung imaging. High resolution lung imaging is really, really good and it's getting better. But I think there's still a lot of advancements getting these structural information. The CT system, in my opinion, there will not be a dark field modality. I think it will be a CT scanner which has the capability of doing also dark field when it's needed or phase contrast. Now your question in the relationship to MRI imaging. I mean, it has been shown on synchrotrons that the soft tissue contrast you can generate with phase contrast is comparable to MRI. I think this is a long, long way to go. I mean, we have to develop a lot of grating technology to get there, even if we ever get there. So I don't think that's an intermediate. If I would do MRI research, I would not stop right now because somebody's doing phase contrast, to be very clear.
Thanks.
Maybe you should send an email to those MRI researchers.
Yeah, right. You can stop. It's not worth your time anymore.
Hey, Peter, it's Jonathan Maltzer from GE. Thank you for the great talk. Does this diffuser method change any of the requirements on the gantry dimensions, the source to object and source to detector distance?
So you start to stretch out again. So you need a longer distance because you want to propagate a specific distance that you can see those speckles. It's not as bad as propagation-based imaging, but it's also not as great as grating imaging when it comes to gantry and how to bring things together. I think there is this. I think now we are at the spot where we showed we can do it with the ideal grating, but now we can also think about other ways of doing it. Maybe there's also a combination. Maybe it can be a speckle grating combo, for example, which could work, which maybe releases some of the issues. So I think still to be determined how this will play together later.
Right, I see. Thanks.
But did I understand correctly, just to evolve, to dwell a little bit there on Jonathan's question? So if we stick to grating base, then you don't see any fundamental reason why the dimensions of the CT need to be changed, like some.
No, I think I think some results, including the one I just showed from China, show that conventional CT gantries should be able to handle this from sizing. I think I don't see a stopping point there. I mean, of course, if you could make the gantry not 1 but 2 meters in diameter, the results are probably better because the more we propagate, the better it is. But I think you can get to sufficient results, or I believe you can get to sufficient results with it, with a conventional gantry setup.
And vibration, I mean, how much of a problem would vibration be in a practical CT?
It's a good question. I mean, you can see from the results we see, you see that the vibration, which for example comes from the tube, doesn't play a role because all these people showed large images with rotating anode tubes. So I think that's one of the ones where the frequency could be a problem. You also see that other vibrations should be handleable, but I'm pretty sure that there will be some correction work or correction software or algorithmic solution to address this. But nothing, from my perspective, there is of course vibrations which be deadly, but what all these results showed us that there is probably a good mode of working where it should work with the vibrations.
It's very interesting. So I mean, you know, we've been looking at this, well, I've been looking at this only for a short amount of time, but seeing the amount of progress in the last few years, it's sort of really begs the question, what should we be doing? What should a manufacturer like GE be doing as far as phase contrast? And you know, what do you think the next step would be from our point of view?
I mean, I think there is a couple of things you can observe. I mean, there is a handful of groups which center around the Munich group who started and pushed this, but now you see it spilling over. Others see this and say, this seems to work and it's an interesting topic. So they're starting to invest their time into it. So I think we did the breakthrough that people believe this will happen. With this, I think, as every technology, I think if I would be a large company, like GE in this case, I would keep a close eye on it and would start to think about where are we and how do we want to be part of this. I mean, it's known that others have invested into it at different sites. So yeah, I think it's time to think about it.
Any more questions? We are reaching the hour here, and we had a lot of questions already, but maybe there are a few more pressing items. Now is your chance.
You can always write me an email. I'm
There you
happy
go.
to meet again and talk more. No worries.
There you go. Okay, so Peter, thanks again. Fantastic lecture, and of course, welcome to Stockholm anytime.
I will wait until it gets a bit warmer.
Yeah, I would think so.
We're all waiting.